Most people, whether medical doctors or not, know that the human body encounters a variety of internal and external pressures on a minute-by-minute basis. Many practicing MDs go on to make thousands of patient diagnoses, ranging from the yearly flu to the rarest of infectious diseases. After a thorough analysis of symptoms, they say with seemingly complete certainty that a patient has condition X. Yet, in some cases, a simple statistical calculation can help us question the immediate validity of some of those judgments. Today, I'm going to introduce you to Bayes' theorem, a simple yet applicable method that can help physicians make their medical decisions. Let us look into a question that a Harvard Medical School professor posed to his students. 1 in 1,000 people has a prevalence for a particular heart disease. There is a test to detect this disease. The test is 100% accurate for people who have the disease and is 95% accurate for those who don't. This means that 5% of people who do not have the disease will be wrongly diagnosed as having it. If a randomly selected person tests positive, what is the probability that the person actually has the disease? 100% accuracy, 95% accuracy. Many guess that based on these numbers, the answer must exceed 90%. The true answer, in fact, is less than 2%. This seems to make no intuitive sense. For now, though, let's look into some background before showing you the formula. Bayes' theorem was developed by Thomas Bayes back in the 18th century. But the English statistician and philosopher ironically never presented his work and derivations because they just seemed to be too simple. Just a few years after his death, though, his work was discovered and presented to the Royal Society, and the rest is history. Today, Bayes' theorem is applied in supplement to a variety of situations. In the courtroom, attorneys have attempted to use it to define the likelihood that someone is innocent, given a set of evidence. The theorem has been applied to algorithms to identify spam emails, predicting weather, financial investment forecasting, environmental damage given previous events, you name it. In the biomedical world, Bayesian inference has been employed in predictive infectious disease phylogeny by accounting for horizontal gene transfer events, as well as different forms of molecular evolution. In addition, a tool called Batman has been developed to detect methylation in different compounds via the use of Bayesian statistics. But let's say that you are a practicing physician attempting to diagnose a disease. Up to this point, none of the examples or applications have seemed very useful in your line of work. Well, Bayesian statistics still holds serious significance. The World Health Organization during the mid-2000s used a rigorous implementation of Bayes' theorem to analyze the causes of maternal deaths worldwide. Given any large amount of data, complex modeling algorithms can be used to understand the relationships between different variables and reduce the information down to a few predictive correlating variables. But more simply, given a prevalence rate as well as a false positive and false negative rate, we can determine the likelihood that a person has a condition if he or she tests positive for the disease. Let's briefly look at the theorem. Given sensitivity and specificity measures, one can easily determine false positive and false negative rates. Sensitivity is the true positive rate, which means that the false positive rate would simply be 1 minus sensitivity. Specificity is the true negative rate, so the false negative rate would simply be 1 minus specificity. Okay, here is the formula. As you can see, there are three underlying variables that we need: A, B1, and B2. A patient comes in to test for disease. The patient either has the disease or does not. So that means when a patient comes in, he or she will either test positive for having the disease or will test negative and not have the disease. So for a medical diagnosis implementation, we'll say that B1 is the event that a disease is present in the patient, and B2 is the event that a disease is not present in the patient. So this means that PB1 is the prior probability that a disease is present. In other words, without any previous information, this is our national prevalence rate for the condition. PB2 then becomes the probability that the disease is not present in the patient. This will be 1 minus the national prevalence rate for the disease. Now our third variable, A, is the event that a positive test result is achieved. So P of A given B1, reading across that term, is the probability that a positive test result comes back given the event that a patient has the disease. This, in other words, is our sensitivity value, or the true positive rate. P of A given B2 is the probability of getting a positive test result given the fact that the patient does not have the disease. This, in other words, is our false negative rate, which is 1 minus the specificity value. And what we're solving for is P of B1 given A, the updated probability that a patient has the disease given that positive test result. It's interesting to note a criticism of the application of Bayes' theorem. Some say that using the national prevalence rate as our prior likelihood is misguided, that diagnosing a random patient from a population set is too generalized. I mean, why is it useful if we bring a patient in with very obvious symptoms? That's not a random patient at all. Yet, what many people fail to realize is that there is an inherent bias of coming into the doctor's office. First of all, the patient could have very obvious bias or misguided outlook on the symptoms. Those same symptoms direct the physician's diagnosis, and those symptoms could overlap between multiple different conditions. This means that some conditions are overdiagnosed because of inherent human error. Bayes' theorem removes these biases altogether by taking into account the national prevalence rate as our only prior knowledge. So, how could you use this information to help with patient diagnoses? In the next video, we will apply these prevalence rates and diagnosis accuracy with Bayes' formula using an interesting heart-related condition. I'll see you there.